Um, it's a pleasure to welcome you all for our morning seminar today, because it's in the morning because our speaker is from the West Coast, and we are going to hear from Shreya Vardhan today about Petz recovery from subsystems and conformal field theory. Over to you, Shreya.
Okay, great. Yeah, thank you so much for the invitation to speak. And I'll be talking about this recent paper with Annie Wei, who is a grad student at MIT, and Yejian Zhou, who is a postdoc at Stanford. And please feel free to stop and interrupt me with any questions at any point. Oh, sorry, it doesn't seem to be going to the next slide. Okay, good. So let me start with some background and motivations about this problem. So I'm going to be talking about some aspects of multipartite entanglement in the vacuum state of a CFT. But before doing that, let me review some more familiar facts about bipartite entanglement. Okay, so if we have any pure state psi in any quantum mechanical system, we can divide that system into two parts, A and B. And we can look at the entanglement entropy between A and B in this state, which is defined as follows. You look at the reduced density matrix on the subsystem A, and then take the log of rho A and the trace in this way. Okay, so this quantity has a very clear operational interpretation in terms of measuring bipartite entanglement between A and B, which is as follows. That if you consider all possible local operations in the systems A and B, and all possible classical communication between them, this is a set of LOCC operations, then there's some maximum number of EPR pairs that you can distill out between the systems A and B by doing such operations. And this number is exactly equal to the entanglement entropy between A and B. Okay, so this quantity has a very precise operational interpretation. And another thing that is useful about it is that it takes a very simple and universal form in a lot of physically interesting situations. So one such setup is if you consider a single interval in the vacuum state of a conformal field theory in 1+1 dimensions, then the entanglement entropy is always given by this simple formula, where C is the central charge of the CFT, LA is the length of the interval, and epsilon is the UV cutoff on the theory. Okay, so this simple expression tells us a lot of useful things about the entanglement structure of the vacuum state. One thing we can notice is that we get a divergence as the UV cutoff goes to 0. And this divergence tells us about the presence of a very large amount of entanglement at short distance scales in the vacuum state, such as from short distances close to the edges of A. Okay. The second thing that we can observe is that as you increase the size of A, this entanglement entropy grows. So this tells us that there is also entanglement present at longer length scales, which I've represented with these kind of simple bell pairs between points that are at farther away distances. Okay, another thing that is interesting about this is that it only depends on the central charge of the CFT, but not on any of its detailed operator content. So it's a universal expression in any 2D CFT. And this universality has been very useful for applications such as starting with this expression and motivating the definition of a C function in any relativistic QFT in 2 dimensions, which is a function which behaves monotonically under RG flows. And it was also useful for motivating the RT formula, which identifies a bulk dual of this quantity in ADS3. Okay, and there are many other applications in condensed matter systems. So the quantity that I will discuss today shares the features that it also has a precise operational interpretation, and it is a universal quantity in any conformal field theory in 2 dimensions. So the question that we'll consider is as follows. You consider, again, the vacuum state of the conformal field theory, and you consider its reduced density matrix on 3 adjacent regions, A, B, and C. Okay, so based on the formula that I showed on the previous slide, we can make a simple model for the entanglement in this state between A, B, and C, which consists of a lot of entanglement on short distance scales between A and B and C, as well as longer range entanglement of this bell pair kind between A and B or A and C and so on. But it turns out that this picture is too naive. And this has been observed by looking at a variety of different entanglement measures, such as reflected entropy, that the state doesn't have simply this kind of simple bipartite entanglement structure among the three regions. But one drawback of quantities like the reflected entropy is that their operational meaning is not very well understood. In today's talk, I will probe the multipartite entanglement structure by asking the following question. If you have three such regions, A, B, and C, then to what extent are the correlations between A and C in this state mediated by B? Okay, so in particular, in this toy model that I drew, all the correlations between A and C are just direct correlations. There isn't really a notion of correlation mediated by B in this state. Okay, so in order to make this question more precise, we can consider the following operational setup. So we start with the reduced density matrix rho ABC. And then in this state, we throw away or trace out the subsystem C. So then we're just left with rho AB. And now we want to try to act with some channel on this state, but this channel should act non-trivially only on the region B, not on A. And by acting with such a channel from B to BC, we want to reconstruct some state rho tilde on A, B, and C. Okay, so the question that we'll ask is, how close is the reconstructed state rho tilde ABC to the original state rho ABC? And in particular, if the state is closed, then that means that all the correlations between A and C were mediated through B because we were able to reproduce them just by acting on B. So one thing you can convince yourself of is that if I had a state with this kind of bell pair structure, then by acting with any channel just on B, I would never be able to reproduce the bell pairs between A and C. Okay. Good. So the first question that we can ask before considering this for general setups is just whether there are any setups in quantum field theory where this recovery can be perfect. So are there any setups where rho tilde ABC is exactly equal to rho ABC for some choice of this channel? Okay, any questions about this, the setup or the problem at this point?
I have just a small question. If I guess you are going to say this, that if you have the, what is it called, this this product that A cross the subsystem of B that is maximally entangled with C, and the subsystem of the B is a direct, what is it called? I forgot.
A direct product of systems, and there's some are entangled, some are entangled.
Yeah, so it is B has to, B is equal to B1 plus B2, where B1 is maximally entangled with A and B2 is maximally entangled with C. And so in those cases, of course, you can always perfectly recover, right? I mean, this kind of.
Exactly. So if there were no such bell pairs between A and C in this state, then you would be able to perfectly recover the entanglement between B and C, because all you need to do is entangle B with C.
I see. So if, okay, so you're saying that now, so if you had only BC system and you're able to trace out C, then there, of course, there is this maps like Petz map that can recover it. And the question now is, in presence of another state A, how well the recovery map works, the usual recovery map works. Is that a question that you're asking?
Yeah, exactly. So for this setup, and even in the case where you have A, and even in the case where there are some correlations between A and C, it actually is possible to recover some such correlations if they have a particular structure. So I'll talk more about this later, but some certain kinds of correlations between A and C can be recovered just by acting on B. Although this direct bell pair type of correlation can't be recovered. So looking at this question will tell us about the nature of the correlations between A and C.
I see, thanks.
Great, any other questions? Okay. So like I said, we would first like to see if there are any setups where you can have perfect recovery. And indeed, the answer is yes, even in a quantum field theory. And this setup was identified by Cassini and Huerta several years ago. So again, we consider the vacuum state of a CFT, and we take A, B, and C to be three adjacent intervals, but now we take B to be an interval on a spatial slice, and A and C to be null intervals on either side. Okay, so in this specific setup, you have the very special property that if you look at a quantity called the conditional mutual information, which is defined as this particular combination of the entropies, then this is exactly equal to 0 for any lengths of these A, B, and C. Okay, and it's simple to see this. You can see this just by using Lorentz invariance, so that, for instance, the entanglement entropy of A union B is equal to the entanglement entropy of this dashed space-like region. And then you also use the fact that the entanglement entropy in a Lorentz invariant theory is a function only of the Lorentz invariant length, and apply the formula that I mentioned on the previous slide, or on the first slide for the universal entanglement entropy. So just by using that, you can see that the conditional mutual information in this setup will be equal to 0.
Can I ask why it is important that A and C are null in this argument?
So this vanishing happens only for the case where A and C are null.
I see, just a matter of geometry that.
Yeah, it's just related to the geometry, and like once you, it's related to the geometry and the fact that you're looking at this particular combination of the entropy.
So it means that the length of AB plus the length of BC is the same as length of B and length of ABC. So that happens if this particular A square and C square vanishes. Exactly. I see. So that would be simply a geometric statement of that. I see. But in this context, it means that it's a kind of the state. There is a theorem that was proved that if this happens, the only way it can happen is that there is this A cross. This can happen because there is some what is it called? The subspaces. The direct sum. B is a direct sum of B1 and B2. Where B, so
yeah, exactly. I will actually be mentioning that just on the next slide. So yeah, but you're saying that the state has a certain Markov state structure, which is very
exactly. Yes.
Yeah. So exactly. So this vanishing of the conditional mutual information is equivalent to two things. The first thing that was shown in this paper by these authors in 2005, that the first thing is that this recovery task that I mentioned is possible with perfect recovery. So, and in fact, not only is it possible, but you can write down an explicit form of the channel which accomplishes it, which is called the Petz map. So in this channel, you act with rho B to the -1/2 on both sides of the input, and then act with rho BC to the 1/2. Okay. So the vanishing of the conditional mutual information tells you that the state rho tilde ABC, which you construct by acting with this on rho AB, is equal to rho ABC. In the setup, you also know that the state has the Markov state structure, which means that there exists some direct sum of direct products between some B1I and B2I, such that you can write the state rho ABC as a sum of tensor products, which look like this. Okay, so once the state has this structure, then you can see why you should be able to recover the whole state just by acting on B, because suppose you trace out C, then this is the state that you get. And you can restore the original state just by some channel that acts on B and sends each of these rho B2Is to the appropriate state rho B2IC. And apparently the Petz map that I wrote down on the previous slide accomplishes this task. Okay. Another thing that you can notice about this state is that it's once you trace out B, you get a separable state between A and C. So it's just some mixture of tensor products between A and C, which means that it does have some correlations, but these correlations are of a purely classical nature. There's no quantum entanglement in this state. And this is related to, the only way that you can have two regions in a quantum field theory which have no non-trivial entanglement between them is if they're null by the Riesz-Leiter theorem, because the Riesz-Leiter theorem tells you that any regions of non-zero volume have to have some non-trivial entanglement. In case that comment didn't make sense, that's okay. This is just a passing comment. But for the conditional mutual information 0 case, this is the structure of the state. Okay. So now we can ask what happens if instead of the setup that I described previously, we consider 3 adjacent intervals on a spatial slice in the vacuum state of a CFT. And again, I can look at arbitrary lengths of A, B, and C, and I can define this particular ratio of their lengths, which I can call the cross ratio. Okay, so in this setup, the conditional mutual information is no longer 0. And it's given by this simple function of the cross ratio, which can again be seen just by using the formula for the entanglement entropy on the first slide. Because for a setup like this, all the intervals, all the regions involved in the definition of the conditional mutual information are just single intervals. Okay, so because this conditional mutual information is non-zero, the quantum information theorem that I mentioned doesn't apply, and the recovery operation cannot be carried out perfectly in this setup. But we
can I ask,
Yeah.
so because in this formula, if I look at it, then it seems that it requires only LA or LC to vanish, but not LA and LC together to vanish. If I just look at this formula, LALC divided by. So, but you said somehow you need both LA and A and C to be null.
Oh, I guess, yeah, if A vanishes, then there is no sensible notion of entanglement between A and C. So if you have some non-trivial regions, and you want there to be no entanglement between them, then the only way is if they're null.
Yeah, but you said that you need both LA and LC to be null, but in this formula, it seems either LA or LC null being fine. The formula that you just wrote later. So the cross ratio.
Yeah. Yeah, it might be that you need, so this formula that I wrote was specifically for the case where they're on some spatial slice. Maybe there's some slight modification of it because you also need like the complex conjugate of eta in that case, where they're not, and it might be a more complicated formula in that case.
Okay, fine.
I'm not entirely sure if this also works in the case where one of these is null. I would have to check.
Okay.
Yeah, but if you do consider the case where A, B, and C are all on the same spatial slice, then this goes to zero only in the limit where A and C are very far from each other compared to their sizes.
Yes.
Right. So now we can ask, in the setup where the conditional mutual information is non-zero, is it still a good quantitative measure of how well the recovery works? And to some extent, the answer is yes, because we can show this general inequality in any quantum mechanical system. That if you define some generalization of the Petz map state that I defined before, where basically the only difference here is that we replaced the 1/2 and -1/2 with 1/2 minus I lambda over 2 for some real number lambda. And similarly, we've made similar changes in all the other exponents. So this is some generalized version of the Petz map, and we can consider the fidelity between rho ABC and rho tilde lambda ABC and maximize this fidelity over all lambda. Then this is lower bounded by this quantity in terms of the conditional mutual information. So the fidelity is a measure of distance between two states, which is equal to 1 if the states are identical, and it goes to 0 if the states are orthogonal to each other. So this inequality tells us that when the conditional mutual information is close to 0, then we get a very good bound because the fidelity has to be very close to 1. And this happens in particular in the regime where the intervals A and C are very far apart, so that the cross ratio goes to 0. But more generally, if the conditional mutual information is large, then this doesn't really give us a very meaningful bound because it just tells us that the fidelity is greater than 0, which is always true. So if we wanted to have a direct quantitative answer to the operational question that I mentioned previously, then we should directly evaluate a quantity like the fidelity between rho and rho lambda and see how it compares, for instance, to this quantity. Okay, so that is one of the things that we're going to do in this talk.
Just Shreya, one question. So is there, because you wrote greater than equal to, is there understanding that for an appropriate choice of lambda, you can always saturate this inequality? Yeah, that's a good question. So it's not known whether you can saturate it or not in general. And
In fact, in the system that in this CFT setup, you'll find that it's never saturated. There can be some special situations for other kinds of states that you can write down where it is saturated. But in general, it's not saturated.
Okay, thank you.
Yeah, and then later we'll also, like, I'm not mentioning this explicitly here, but there's also a version of this bound which involves an average over the log of the fidelity overall values of lambda. So there's both a version in terms of the maximum and in terms of the average. Yeah, in contrast to this statement, this Markov state structure is actually not robust. So if the condition mutual information is non-zero but small, it's not possible to make any statement about the state being close to a Markov state of the structure. So the only statement which is robust is the one in terms of this recovery. Okay, so what we want to do is evaluate the fidelity between rho ABC and rho tilde ABC for this particular combination of the reduced density matrices. And in fact, we'll evaluate not only the fidelity, but also the relative entropy and the trace distance, just to build a more robust picture of the difference between these states. And what we'll find is that even though these different distance measures have different interpretations, especially the fidelity and the relative entropy show very similar behaviors. And in all cases, we'll use the explicit 12-paths map that I wrote down on the previous slide. And the approach that we'll take is that we'll use a replica trick to express each of these distance measures as a 4-point function of some twist operators in the symmetric group on some number of copies of the system. And one of the main results is that each of these distance measures will turn out to be independent of the UV cutoff, unlike, for instance, the expression for the entanglement entropy that I wrote on the previous slide. And at the same time, they will also be universal with respect to the operator content of the theory. Okay, and this should be somewhat surprising because in general, a 4-point function of some primary operators in a CFT is not independent of the operator content, but it will turn out to be true for these particular quantities.
So you mean here it doesn't depend on the 3-point functions, just on the yeah. Spectrum? I see.
No, it doesn't even depend on the spectrum. It only depends on the central charge.
Okay, I see.
Yeah. So at that level, it's similar to the expression for the entanglement entropy for a single interval, which depends only on the central charge. Yeah, and then we will also use the OP of these twist operators to explicitly find the behavior in the eta going to 1 limit, where the intervals A and C are very close to each other. And then the other thing we'll do is evaluate these quantities numerically for all values of the cross ratio by using various critical spin chain models, because once we know that this is a universal function for all CFTs, then we can just evaluate it in any particular CFT. And we can also check this universality. And one result that we find is that in all regimes, like I mentioned, the bound on the previous slide is not saturated. So the fidelity is always better than the conditional mutual information lower bound. So all of this is telling us about some quantitative differences between the state rho ABC and rho tilde ABC. And finally, I'll also discuss some more qualitative questions about exactly what is different between these two states. So for instance, does rho tilde correctly capture, or to what extent does rho tilde have the same correlations as rho between A and C or between A and B? So that'll be the final part of the talk. Okay, so the plan will be to first explain the twist operator method for the fidelity. We use a similar method for all the different quantities that I mentioned on the previous slide. So just as an example, we can go through the fidelity in detail. And then I'll summarize the numerical results for the fidelity and the relative entropy from our lattice simulations. And I'll discuss the OP limits in the twist operator formalism, which explains some part of these numerical results. And then finally, I'll discuss the qualitative differences between rho and rho tilde. Okay, so any further questions at this point? Okay, great. So let me first describe the replica trick that we use for calculating things like the fidelity between rho and rho tilde, which is a more complicated version of the same kind of replica trick that's used for the Renyi entropy, for instance. So the definition of the fidelity between any two density matrices rho and sigma is this somewhat complicated expression, which for pure states rho and sigma just reduces to the overlap between the states. And it's not obvious, but it's possible to show that we can also write this as trace of rho times sigma to the power of 1/2. Okay, and then we can introduce a replica trick where we promote this 1/2 to some integer k, and try to evaluate this as some function of this k based on the integer values, and then analytically continue that to k equal to 1/2 to find the fidelity. So you recall, so now we want to calculate the fidelity between the particular states rho ABC and rho tilde ABC. And the definition of rho tilde involved various powers of -1/2 plus I lambda over 2 and plus 1/2 minus I lambda over 2, etc. So we also introduce a replica trick for each of these powers and replace them with some integers. So overall, we have 5 different replica indices. And the thing that we want to calculate is this combination of powers of various reduced density matrices. Okay, so the strategy is to find this for integers and then send the resulting expression to these values, which we call the replica limit.
Do the order of these limits matter on the various?
In practice, we find that it doesn't matter for any of the calculations that we did. Yeah, but it seems, yeah, it's more sensible to define them in this order because if you just simultaneously make all of the parameters complex, then this thing is not well defined. Because if you have some matrix with complex eigenvalues, then it's not well defined to take its power of k, etc. So that's the reason for writing it in this order. But the actual functions that we evaluated doesn't really matter. Yeah. So, okay. So now this is what we want to calculate. And again, we use a more complicated version of the trick that is used for the Renyi entropies. So this involves some number of copies of the density matrix of the vacuum state. And in the different copies, we've traced out different regions, and then we multiply the matrices in this order. So the first thing that we use is that that each of these copies can be given a Euclidean path integral description from -infinity to infinity, where we specify what states we're taking the matrix element between by the boundary conditions at tau equal to 0. Okay. And now in order to trace out a certain subsystem, we would glue together these states in that region and so on. So we have some rules for how these n times k copies, where n is given by m1 plus n1 plus n2 plus m2 plus 2. We have some rules for gluing together these copies, and because the different regions play a different role in this expression, we get different rules for how we should glue together the copies in A, B, and C, and the complement of ABC. Okay, so based on those rules, we just get some complicated path integral on n times k copies. And we can work out what permutation we should use to glue these copies together just by looking at this expression. So one simple thing that we can observe is that the matrix B is not traced out in any of these copies. And as a result of that, we should just successively glue together phi1 prime to phi2 prime to phi3, and so on. So we just get one big cycle in the permutation in B. Okay, so what do we do with this expression? It looks very complicated. The first thing that we should do is rewrite this as a 4-point function of some twist operators on nk copies of the theory. Okay, so a twist operator associated with some permutation tau in the symmetric group is defined by the fact that if this is inserted at the point P, then if you take the fields around the point P, then you're sent from the copy I to the copy tau of I on going anti-clockwise. Okay. And it's possible to see that
How do you get the symmetric group?
you get the symmetric group because essentially just because these are permutations which are no longer just in Zn. For instance, this tau B inverse tau A permutation that you get from composing tau B
But
and
it
tau
could be some subgroup, right? It could be some subgroup of SNK. I agree that it will be something bigger than cyclic.
Yeah. You mean that once we look at these four permutations, the group
Yeah, you put them together and
yeah, that is possible. I'm not sure that that's very important for our discussion.
Okay,
But
okay.
whatever you get is some non-abelian group. So
yeah, okay.
yeah. Right. So good. So you have these yeah. So basically by the rules that you use to glue together in the different regions, you can see what happens when you go around a certain point at the junction of two of these intervals. And from doing that, you can identify that you get twist operators at the endpoints, which are the ones at the endpoints x1 and x4 are simple. They're just expressed in terms of tau A and tau C. But then to find the ones at x2 and x3, you need to compose tau B inverse with tau A and so on. So these permutations that appear here have multiple cycles. And yeah, this is one example, for instance. So this kind of picture is supposed to show that this element goes to this one, and this element goes to this one, etc. And if there's an element which is not part of a cycle, then it's just sent to itself. Okay, anyway, so you can identify some permutations in this way, and now you have a 4-point function of some twist operators. And now we can use general facts about such twist operators in a conformal field theory. So in particular, we can use the fact that the twist operators are primary operators whose dimensions are determined entirely by their cycle structure. So if the permutation tau has m cycles, which have lengths a1 through am, then the dimension is given by this formula. And
I'm sorry, can you explain to me how you get the cycle shape?
how you get the cycle shape?
I was maybe dozing off and you tried to explain this picture of
Oh,
the
yeah,
bottom
I
of this slide. I'm really sorry.
No problem at all. So you mean how you identify that you should get tau B inverse?
Yeah. What is the cycle shape of some picture, I mean, or yeah, how do I see that? I mean,
You mean what cycle structure does this picture
no,
correspond to?
here I can see it. I mean, I can just read off,
Uh-huh.
Right? I mean, you've written it in this form, but how do I quickly get this? Tau B.
It's not very quick, so you need to basically you need to compose tau B inverse here with tau A.
Okay. Okay.
So you just kind of follow the cycle, like yeah.
Okay. So what's happening is that a particular configuration picks out a particular conjugacy class of SNK. Is that what is happening after you compose tau A, tau B inverse? Conjugacy class is cycle shape, but same thing.
Yeah. Right. You get a particular, but one thing is that these.
But as you vary M1, N1, this thing, you get all possible shapes. Is that?
Not necessarily. You always have the structure where in tau B inverse tau A, you have k cycles of length m1 plus n1 plus 1 and k cycles of length m2 plus n2 plus 1. So you can vary the lengths by varying n2.
So if you keep M1, N1, M2, N2 fixed, you get a particular cycle shape, right? That's the point.
Yeah.
Okay. Thank you. Sorry to be so.
No problem. Yeah, one thing related to what you mentioned though is that so these are somewhat different, I guess. Yeah, sorry. So the twist operators appearing here, we're not doing a sum over different elements of the conjugacy class. So these are these sort of come with these Wilson lines or branch cuts, which
Yeah, I get it. So what it looks like is that you have like a cross of suppose each cycle will give you a cyclic at the end of the day, looking at your formula also, it's just as if there were like it's Z A1 cross Z A2 cross so on and so forth, where A1, A2 are the cycle lengths. Is that correct? I mean, then you write this formula for the twist operator as the sum of those.
Yeah, right.
Right?
Exactly.
Is
So
that the correct interpretation?
um yeah, you should think of it as
So suppose it had just one length n, like we do in the classic RT story replica trick, that AI would be just n minus 1 by n, right? I mean,
yeah,
that's
exactly.
what you're
Right.
okay.
And here
Okay,
you
so
can one simple way to understand this formula is just that there are just m such things which are next to each other. So you
Yeah.
just end up adding their dimensions.
Yeah, okay.
Yeah.
Okay, thank you.
I have one question about this. Because you are just simply identifying ultimately a 4-point function of this with certain number of cycles.
Yeah.
So I'm wondering if the order in which you are writing, for example, this row, this particular thing, is there different kind of orderings will give you the same correlation function or?
No, different. Like if I put row AB here instead, or if I put row AB between these, then I would get some other permutation. And probably then when I compose that tau A with tau B, then I would get some other cycle structure as well.
Yeah, I see.
So this is very particular to, because I put row AB at these locations, that's why I got this particular structure of the permutation in A. And then that determines how many cycles of which kind I have in this.
Yeah, okay.
Yeah.
And it's, if you just tell me M1 and M1 N1 and N2 M1 M2 N1 N2, you then know this 4 and then if you vary, then all the 4 dimensions will change. All the
That's right.
dimensions.
Yeah.
Yeah. So there is no combination of okay. It's okay. Thanks.
Right. But yeah, one thing that you can observe is that if you plug in the cycle structures, which I haven't described all the cycle structures of these 4 permutations, but for each of them, you can see that if you plug into this formula and then take the replica limit, so that was when I was taking these particular values of K and N1 and N2, M1, N2, then I find that each of these dimensions just vanishes in the replica limit. Okay. So one consequence of that is that this quantity is, the fidelity is a UV finite quantity, because in this, in principle, this 4-point function was not normalized. So it would have some UV divergence for general values of these Mi, Ni, and K. And in order to cancel the UV divergence, I would need to divide by a 2-point function of tau A with itself and 2-point function of this thing with itself and so on. But because all the dimensions are vanishing in the replica limit, that factor which is supposed to cancel the UV divergence is going to 1. So that tells you that this quantity by itself was already UV finite. Okay. And this is kind of interesting because the formula that I wrote down for rho tilde involved like a combination of the reduced density matrices on AB and BC and B. And if you made some simpler combination of these reduced density matrices, then the fidelity of that with rho ABC would just go to 0 in the continuum limit. So, the simplest thing you can try to do is look at the fidelity between rho ABC and rho A tensor rho BC. And this fidelity would go to 0 as you take the UV cutoff to 0. And the interpretation of that is that a state like this is missing the very large amount of short distance entanglement between A and B. So somehow, even though this rho tilde state was constructed from reduced density matrices on various subsystems, it's somehow a very clever combination that is able to capture all the short distance entanglement structure between A and B and between B and C. Okay, so the second thing that I wanted to emphasize was that the 4-point function that corresponds to the fidelity is universal and doesn't depend on the operator content of the theory. So in order to do that, we need to first discuss a little bit more about how to evaluate this kind of 4-point function. Because of the presence of the twist operators on the original space, the fields are multiple valued. So we call the original space the base space.
Sorry, I just have one question.
Yeah,
What if I do the fidelity of row ABC with row B cross row AC, row B times?
That would also miss the entanglement between A and B and C at short distance scales. So that would also go to
Yeah.
0.
Oh, okay. Okay, A and B and sorry, yes, sorry. It will still miss the.
Yeah.
I see. Okay. So okay. Thanks. Thank you.
Yeah. So somehow this combination is very clever because it's basically, you can kind of see that because it contains row AB already, as long as you're not destroying the short distance entanglement between A and B, it's going to be present in the final state. And then one other feature of the state is that if you trace out A, you can see just by this definition that the reduced density matrix on BC is the same as the original state. So somehow this way of putting together the density matrices is able to capture all the entanglement structure that's just between A and B and just between B and C.
Okay, the other point I didn't get, why you're saying that, so because lambda is arbitrary, so I didn't understand this. In the replica limit, all dimensions go to 0. I mean, why doesn't it depend on lambda? Where is the lambda dependence coming in?
Yeah, that's a good question. Somehow, yeah, one thing you can see here is that the cycle length of this cycle is M1 plus N1 plus 1. And more, or you get M2 plus N2 plus 1. So those are the things which go into this formula. But now if you look at the definition of the replica limit, then in M1 plus N1, the lambda dependence cancels out. And in M1 plus N1, the lambda dependence cancels out.
I see.
And M2 plus N2 also it cancels out, and so on. And then in other cases, you'll get combinations of M1 plus M2, and there also it cancels out.
I see. So it depends because of the particular ordering that you have chosen of this rows. This cycles only depend on combinations that where lambda cancel out. I see.
That's right. Yeah.
I see. But then this is a bit surprising that your claim is somehow the fidelity. I mean, this row ABC would be. I mean, this Petz map is completely lambda independent, or if I understand, or is it?
Yeah, that's also a really good question. So far, we don't know whether it should be lambda independent or not. Although from yeah, let's discuss this a little bit later. So from the analytic argument, it does seem like it should be lambda independent. But in practice, we find from evaluating it numerically that it's actually not independent of lambda. So there are some discrepancies between the numerical and analytical results, which I'll mention as we go on. But yeah, let me mention that at a later stage because it'll be easier to mention there. But yeah, the fact that these dimensions all go to 0 tells you that for any value of lambda, this quantity should be UV finite, which is correct. So at this stage, there is no discrepancy. Okay, good. So in order to actually evaluate this kind of 4-point function of twist operators, or any n-point function of twist operators, what we can do is that we started with this with these twist operators on some base space. And because of the twist operators, the fields were no longer single valued. So for instance, at the point x1, we inserted a permutation tau A, which had a cycle with 2k elements. So that means that if you go around the point x1 once, then you don't come back to the original field. And in order to come back to the original field, you have to go around this 2k times. So somehow the strategy that we want to use is to go from this original space and map it to some so-called covering space on which the fields again become single valued. And the way that we do this is by having a map which locally looks like it's proportional to the original coordinate. Sorry, if t is the coordinate on the covering space, then the original coordinate z locally looks like t to the power of 2k. So what this does is that going around by an angle of 2 pi here corresponds to going around by an angle of 2 pi over 2k here. So that when you go around by an angle of 2 pi on the covering space, then you come back to the original field. Okay, so this is nice because the path integral on the base space with the twist operator insertions is equal to the path integral on the covering space, which now doesn't have any more twist operator insertions. But the way in which the covering space captures the presence of the twist operators here is by the fact that it has a non-trivial metric, which is induced from the original space by the fact that this function z of t is some non-trivial function. And in general, it can also have some non-trivial topology. So the path integral on this covering space will be more complicated because of the non-trivial geometry. And this non-trivial geometry captures the effect of the twist operators.
Won't it be just the upper half plane quotiented by some Fuchsian group? So the universal cover, won't it be the upper half plane? Because I think it should be some genus, some higher genus surface, right? With
yeah, that's a good question. So that's immediately what we're coming to next. So somehow it turns out that
I want to ask, what is the genus, for instance?
The genus turns out to just be 0. So and this is not even true just in the replica limit. It's true for arbitrary values of these ni, mi, k parameters that I mentioned. Okay, so the genus is just given by this universal formula in terms of the cycle structures. So what you have to do here is look at all the cycles which are present in all 4 permutations, and then look at the lengths.
No, the covering space will be simply connected and it will have genus 0 by definition. You're talking of some universal cover, right? Of that thing. So it'll have no cycles.
So if I had picked some other permutations, for instance, if I looked at the Renyi entropy of 2 non-adjacent intervals, then I get a non-trivial covering space. But for this particular choice of the quantity, I find that when I plug into the Riemann-Hurwitz formula, I get a genus 0 covering surface.
Okay. You're just saying it's a covering space. It's not the universal cover. Okay. Still, I'm confused, but okay. That's my confusion. That's okay.
Yeah, maybe I don't know what the definition of the. I guess I know what the definition of a universal cover is for a group. Here by covering space, I just mean a space on which the twist operators go away and the fields become single.
Yeah. I mean, I understand that. I understand this construction.
Okay. So it turns out that when I plug in the cycle structures of these permutations, the genus of the covering surface is 0. And for that case, this calculation of the endpoint function of twist operators simplifies. So it just becomes a combination of 2 factors. The first factor is e to the SL, where SL is something called the Liouville action. The Liouville action depends only on this covering map, Z of t. And recall that the only input that went into the covering map is basically what kinds of permutations I have in my endpoint function. So in particular, it doesn't depend on any details of the theory, and it only depends on things like k, n1, n2, m1, m2. So it'll be some function which is determined by the covering map. And then I get some factor of the partition function on one copy of the theory raised to the power of 1 minus n times k. So in particular, in the replica limit, this n times k number goes to 1. So all I'm left with is that the fidelity is equal to e to the Liouville action. And the Liouville action has the structure that it only depends on the theory through an overall factor of the central charge. So so basically this is the result that in the replica limit, we find that minus log of the fidelity is the central charge times some function of the cross ratio, which depends, which doesn't depend on any details of the CFT. Okay. Good. So now, so one thing that would be nice would be if explicitly find what this covering map is. And then we would be able to evaluate this Liouville action analytically and take the replica limit and find this fidelity for all values of the cross ratio. It turns out that there are some difficulties in doing this. So there are some general methods for evaluating what this function z of t should be. And what we do in the paper is we write down some parameterization of this z of t map. And we're almost able to determine what it is up to the location of some pole that it needs to have. And the location, in order to actually find the location of that pole, you need to solve a polynomial equation, which is of arbitrarily high degree for general M1, N1, M2, N2, for which there is no analytic solution. So somehow by using this method, we're not able to explicitly find what this function is. Okay, but what we can do instead is that because we know that it's a universal function, we can just see what it is in the lattice realization of NUC at T.
Shreya,
Yeah.
so as you described, this cycles depend only on certain combinations of M1, N2, M1, M2, N1, M2 that where the lambda disappears.
Yeah.
So of course, by definition, this fidelity should, of course, not depend on it. Depend on the choice of lambda, right? I mean, again, I just
Yeah, right. This
confirming.
was the right place to mention. Exactly. So because this covering map is essentially determined by also the cycle structures, that's why it seems from this argument like whatever function you get from this should not depend on lambda. But at the same time, we're not able to actually analytically continue whatever we get from this method, because it's not an analytic function of these parameters. So yeah, so I don't know. So it's possible to imagine that.
Yeah, because if it depends only on some combinations of M1 and N1 where, you know, lambda vanishes. So by definition, you cannot analytically continue in M1 N1 separately, right? Because you should be able to analytically continue in all of these four variables separately, but there are only certain combinations that determine this function. So you cannot analytically continue on all of these four variables independently, right?
The thing is that even if you analytically continue independently, the cycles only depend on M1 plus N1 and N1 plus N2, etc. So it seems like whatever function you get as a result, this Z of T map will not depend on lambda. But that actually, as I mentioned just in a slide, that turns out to be wrong, and we do see an explicit lambda dependence in this quantity. So this is kind of a puzzle that we don't understand the resolution to.
I'm just saying that if the resolution could lie in the way of understanding analytical continuation, because somehow you have to be able to analytically continue in some of these things separately, whereas this covering map wipes out the separately, only keeps some information of the variable combination of the variables.
Right.
So, I mean, what I'm saying, this replica trick, the way we have the replica trick is defined is unable to see the lambda dependence. It could be the fault of simply because of the cycle structure is wiping out separately M1, N1, and M2, M2. So, I mean, yeah, so maybe another way could be that if you could, or maybe, I don't know, if there is some other deformation you could do such that you could see this M1, N1, M2, M2 separately, and then take that deforming parameter or something like that. I was just wondering if there could be some subtlety here because of this.
Yeah, the problem is that we already started out by allowing all of these to be different.
This I understand. Yeah.
So it's hard to think of a more general starting point. Right?
Yeah, no, I agree that this is a very well-defined starting point where you a priori do not say that a priori this you can just continue M1, N1, and
Right.
M2.
Right.
But
or if there is a nice way of going back to Liouville theory and asking, is there this lambda some deformation in Liouville?
yeah.
Will that realize something?
Yeah, like you mean, is there some other version of
Other version of this, exactly.
other
Yeah,
map?
yeah.
Yeah, that's a good
I
question.
think step one is to ask just in, you have your answer in terms of some 4-point function in Liouville theory. So
Mhm.
is there some deformation which sort of gives you, is equivalent to a twisted Petz map in some sense?
Yeah, yeah, maybe. Yeah,
So
that
that
would
might
be.
be, I mean, so I'm jumping one step, which is to looking at this picture and asking, how do you put in lambda? That's not,
Yeah, it's not obvious, but maybe there's something you can do with that. Right. Okay, but let me show you what we find numerically. So we looked at lattice realizations of 3 different CFTs. We looked at the Ising CFT, the tricritical Ising model, and the free boson CFT. And each of these has different central charges and also different operator contents. But the prediction from the previous slide was that if you look at minus log f divided by c, then it should be the same function in each of these theories. Okay, so this plot is showing 2 different things. One is that it's showing the lambda dependence, which, as you can see, this definitely depends quite strongly on the value of lambda. But each of these plots is actually 3 different plots, although it's hard to see. So the line and the diamonds and the pluses are showing these 3 different theories. And just as we predicted for all 3 theories, for any given value of lambda, this is a universal function of the cross ratio.
So there is also some kind of monotonic dependence on lambda, which is quite interesting. And why do you think for any eta, actually, it seems that there's some monotonic means, do you understand this? Why, or some physical understanding why this should be like this?
No, I don't understand this physically, and it would be very interesting to understand it, but somehow this lambda dependence is very elusive. So yeah, this is something that it would be good to understand, but it seems like the replica trick is not the right way to understand this. But and as far as I know, in the general QI literature, there aren't really general arguments about lambda dependence in an arbitrary state. So it seems like you need to specialize to some many body system or some kind of state and then discuss. And I think there is something more to be understood here. But
and what are the values of N1, N2, M1, M2 for this plot?
oh, here I've taken the replica values, so I'm actually looking at the fidelity. So this is where
okay. Got it.
And that's also why this is UV finite. So in principle, this plot was made by considering a lot of different lengths of A, B, and C. And they all collapse together as just a function of the cross ratio, which shows that this is a UV finite quantity as well. Right. And then I didn't discuss the other distance measures between rho and sigma explicitly, but one other thing we can look at. So there's the familiar relative entropy, which is this kind of asymmetric measure of the distance between rho and sigma. And there's also a 1-parameter generalization of the relative entropy in terms of some alpha, which looks like this. It's alpha going to 1 limit is the usual relative entropy. And for each of these quantities, again, we can define some replica trick. And we find the same feature that I mentioned on the previous slide, that both that these quantities are UV finite and they are universal with respect to the operator content. And then this is a plot which verifies this for the relative entropy, so the alpha going to 1 limit, where again, all of these different curves just collapse together. And the trace distance is yet another useful measure of distance between rho and sigma. And in that case, you don't get some overall factor depending on the central charge, but you can show by looking at the free boson CFT with different operator contents that it depends only on the central charge and the cross ratio again. Okay, so all of these different measures are telling you that the difference between rho and rho tilde is somehow universal.
What are the solid lines in the top curves? Sorry. Solid lines.
Solid line is the Ising CFT. and the other kinds of markers are other lattice. moduli.
Okay, okay. So you have an analytic expression for the Ising, is that the point?
No, it's just shown with solid markers because it's easier to see that there are three different,
Okay. Okay.
but it's not.
I
Yeah,
thought you knew the functional form.
no, we don't.
Okay.
Shreya, I have one more question. You could have also computed this relative entropy or this Renyi relative entropy. And so also from the replica trick, right? I mean, you could have also done, instead of computing fidelity, you could have also done this.
Oh yeah, we did do that. So when we did that, we saw exactly the same features, that it's proportional to C times some universal function, which is now a different universal function. Yeah, so we did do that.
And does it, of course, you only do Ising CFT, but I mean, at least the function that you can get from this method and this replica and the numerical computation, do they agree?
Sorry, so even for the Ising CFT, we don't have an analytic expression. It's just shown as a line on the plot, just as one type of plot marker, but.
I see. So
yeah.
you don't do, yeah, okay, for the, you cannot compute this F-eta actually using
Yeah, so as I'll mention later, you can compute it in one OPE limit, and then we can check this behavior and compare it to the numerics, and it agrees. But yeah, in general, it's yeah, we're not able to do it for general values of eta.
Okay, thanks.
Yeah, but we are able to verify the universality. So whatever the function is, this is what it looks like. Okay, now we can, now that we have this expression, we can compare it to the lower bound from the conditional mutual information. And in particular, so one of the bounds was in terms of the maximum over lambda, which we can see here. The maximum fidelity is just the minimum of minus log f. So it's this lambda equal to 0 value. And then the other expression for which we have a lower bound is a certain kind of average of minus log of the fidelity. So I haven't written down this probability distribution explicitly, but it involves some 1 over 1 plus cosh of lambda or something like this. But anyway, it's just some average. And the information theoretic bounds tell us that both minus log of the maximum fidelity and minus log, the average of minus log of the fidelity are upper bounded by the conditional mutual information over 2. And what we see in this plot is that these bounds are both not saturated. So one interesting thing is that that the average and the maximum have qualitatively very different behaviors. So for this lambda equal to 0 value at small eta, it has a quadratic behavior. But the power law depends on the value of lambda. And if you look at the average, then it has a linear behavior in eta instead of quadratic, which is the same as the behavior of the conditional mutual information. Yeah, so both of the bounds are not saturated, but the qualitative behavior is different between the maximum and the average. Unfortunately, as I'll mention later, we're not able to, like there's some issue with understanding the eta going to 0 OP limit. So which might be related to the fact that it has a stronger lambda dependence. So we're not really able to understand this difference analytically. Okay, so yeah, so just to summarize, in the eta going to 1 limit, just from the general formula, this is what the conditional mutual information looks like. It has some divergence as log 1 minus eta, and with this coefficient. And then the fidelity has a different coefficient in this limit, and also some order 1 and higher order corrections. And the relative entropy, again, has the same divergence, but with some other factor. Okay, and we will be able to explain both of these behaviors by using the OPE expansion. And one interesting thing is that we'll also relate this order 1 correction to some other entanglement quantities, which some of them are, it's obvious why they appear in the OPE expansion, and some other ones it's not. And in the eta going to 0 limit, as I mentioned previously, we observe that the conditional mutual information is just linear in eta. And the maximum of the fidelity, if you take its log, is quadratic in eta. But the average is linear, and the relative entropy is also quadratic for lambda equal to 0. Yeah, and like I mentioned, the replica trick will actually lead to, will not be able to explain these behaviors. Okay, so any questions about these numerical results before I discuss the OP limits? Okay. Okay, good. So let's first consider the eta going to 1 OP limit. So this is the case where A and C are very close to each other and the region B disappears. And in the strict eta going to 1 limit, there is no region B. So the state rho ABC is just rho AC for 2 adjacent intervals A and C. And rho tilde ABC just becomes rho A tensor rho C for this case. And we know that if you look at such a fidelity for 2 adjacent intervals A and C, then it should vanish in the continuum limit because this state is not able to capture the short distance entanglement structure. So we expect that in this limit, the fidelity should approach 0. Okay, so now what we want to find is the way in which it approaches 0 in this limit. So yeah, so because B is vanishing in this limit, x2 is becoming very close to x3. And so we can use the OP between these operators. And this is the usual OP expansion. So it involves some OP coefficients and some conformal block. And then the crucial thing for understanding the leading behavior in this limit is identifying what is the leading primary operator which appears in this expansion. So the lowest dimension primary operator. And in particular, the lowest dimension primary operator appearing in this is not the identity, because we had 2 non-trivial permutations, tau B inverse tau A and tau C inverse tau B, which we're fusing together. And this, because they're not inverses of each other, you get some non-trivial branch cut at infinity from this combination of twist operators. So everything that appears in the OP expansion should also have this branch cut at infinity. Okay. So the identity operator doesn't have this property and it doesn't appear. And the lowest dimension such operator that appears in the OP is simply the bare twist operator tau C inverse tau A. Okay. So I haven't shown this permutation explicitly, but you can see what it is just by composing these permutations. And you can look at its cycle structure and plug into the formula for the dimension that I mentioned to see that in the replica limit, this has a dimension of C over 9. Okay, so then plugging into this formula, this tells us that the leading power here should be C over 9. And the next to leading contribution can also be identified. So because we know that this quantity is universal, the only things that can appear in its OP expansion should be some universal operators, such as these some fractional modes of the stress tensor acting on tau C inverse tau A. And you can identify what the lowest dimension such operator is, and that gives you some dimension of C over 9 plus 2/3. Okay, so so this is the prediction for the behavior based on the expression that I wrote down in the previous slide, where B0 and B1 are just some coefficients. And we verified that this is exactly how this quantity behaves in that OP limit. So basically here we're looking at the fidelity as 1 minus eta goes to 0. And we plot it as a function of this. And this is for the Ising model where C is equal to 1/2. And basically the fact that these are straight lines means exactly that the fidelity has this functional form. Okay, so we're able to find a very clean matching to the kinds of operators that we expect are contributing in this OP limit. And we can also go further. So we can not only identify what these powers are, but we can also give an understanding of what this coefficient is. This is some combination of the OP coefficients. So here the notation 2, 3 OA means that I'm looking at the OP of the operator at x2 and the operator at x3 with the operator, the leading operator in the OP expansion. So anyway, so because this is an OP coefficient, it just involves some 3-point function of twist operators. And now I can invert the trick that I used earlier to express some function of the density matrix as an n-point function of twist operators. I can now go backwards and take this 3-point function of twist operators and identify it as some function of the density matrix. So I can do this for each of these quantities appearing in this expression. And by doing this, I find that this one of these factors, like this F1OA4, is just proportional to the fidelity between rho RS and rho R tensor RS, where R and S are some adjacent intervals. Okay, so it makes sense that this quantity should appear in this OP expansion because of this point that I mentioned earlier, that essentially the whole fidelity is just reducing to the fidelity between rho AC and rho A tensor rho C for two adjacent intervals A and C. But then you can also, there's also some remaining factor, which you can also identify that 3-point function as some combination of density matrices. And that gives some complicated expression, which we don't really have an interpretation of. Yeah, but it's interesting that for some reason, this also appears in this OP limit. One thing that we can observe about it is that if you forget about the original setup where we found this, just look at this quantity. For the case where rho RS is a tensor product of rho R times rho S, then this whole thing for any value of lambda just becomes 1. So it's conceivable that the log of this can be interpreted as some measure of entanglement. But anyway, so this is kind of mysterious what this quantity is and why it appears. But we did numerically check. You can independently evaluate these quantities numerically as well. And this object has some non-trivial lambda dependence. But you can match that for any value of lambda. The value of B0 that you compute from this fitting and the value that you compute from these two quantities matches with each other. So to this extent, the analytic continuation is working and you can reproduce the lambda dependence as well. Yeah, sorry. So I think I mentioned a lot of things here. So if anything was confusing, let me know if there are any questions.
Just one question is, in why only the twist operators dominate? Why only the 3-point function, the twist operators dominate? I forgot, I couldn't follow that.
Oh yeah. So, right, like you might imagine, you mean like you could have the identity operator dominate, for instance, or any other primary operator. The reason for that is that you have some non-trivial twist at infinity from the combination of these operators.
Mm-hmm.
And you have to be able to reproduce that long distance behavior in the OP expansion. So every operator that appears in the OP expansion should have that branch cut. Does that make sense?
Yes. Yeah, I understand. So, so in the limit when eta goes to 1, you always expect that because of the presence of this branch cut, you will always 3-point functions of the twist operators itself will dominate. So that's is that what you're saying?
Yeah. So because in that limit, you have these operators combining into some non-trivial twist operator. Yeah.
Okay.
Yeah. So that's why the lowest dimension thing that you can come up with is just this bare twist operator. Then you can have this dressed with some other modes of the stress tensor. In principle, you could also have this dressed with some other primary operator in the theory, like the lowest dimension primary operator. But if you had that, then you would get a non-universal contribution to your to this quantity, right? Because you would get some power here, which is the dimension of the lowest dimension primary operator. But that can't happen because we already argued that this quantity is genus 0 and universal.
So in the singular limit, of course, when two twist operators fuse, you will have a branch cut that that kind of goes all the way to infinity, and therefore that this branch cut should dominate all the physics in some way. Yeah, so that's respect. Yeah, okay. Okay, thanks. Yeah.
Right. Yeah, and then, yeah, so I guess we discussed the lambda dependence in a few different places. So this was just one thing that I wanted to mention, that even though like we can't get the lambda dependence out of the Liouville action type of reasoning, at this level, like we are able to relate this OP coefficient to another quantity which also depends on lambda. And so you get some non-trivial relation from this OP limit, which does turn out to be correct even numerically. So it's, yeah, yeah. So it's not really, yeah. So we are able to reproduce things to some extent, but somehow
this is surprising because the original expression that you are that we just showed, that you said that has no lambda dependence, but when you're trying to expand it about some limit, you find the lambda dependence coming out. So there seems to be some discrepancy in this. Because you're still expanding you're taking the same 4-point function, your starting point is the same in all cases. So now if you can see it as a partition function on some covering space, partition function of a covering space, or versus you take an OP limit, they give you some different results. So it's
not quite. So I guess yeah, so I identified this F23OA as a function of the density matrix. Then this looks like it depends on lambda, just like the original expression looked like it depended on lambda. But if I directly tried to evaluate, I could also try to evaluate this 3-point function of the twist operators by using the Liouville action method, right? And I could see what the cycle structures are, etc. And again, those don't seem to depend on lambda. So the discrepancy is similar to what you see for the whole quantity. But at the level of relating the different quantities, everything seems to work. Like the original quantity was lambda dependent, and then this coefficient is lambda dependent, and the coefficient gives you the correct lambda dependence of the original quantity. So, so it's just somehow something is going wrong with the Liouville action approach, or like with the covering map approach. Yeah, but
okay.
Right. Anyway, so this was, so basically because we were able to reproduce all of these behaviors in this limit, but now I'm going to discuss the eta going to 0 limit, where, so the first thing is that from the lower bound in terms of the conditional mutual information that I mentioned, we expect that this quantity should approach, the fidelity should approach 1 in this limit. And we are able to correctly see that that is the case. So here we have an OPE expansion, which is similar to what I wrote down before, except that now we're fusing together the operators tau A inverse and tau B inverse tau A, and these two operators. And that gives us some slightly different expansion. And in this expansion, the leading contribution comes from the operator sigma tau B inverse. And this operator has a feature that, unlike the previous case, the dimension of this operator goes to 0 in the replica limit. So the fact that the dimension goes to 0 tells us that the leading contribution in this case will just be some constant. And then in principle, we get corrections to that constant. So this is good because we wanted to see that the leading behavior in this limit is just 1. And in fact, again, by playing this trick of identifying the OPE coefficient as a 3-point function of twist operators and writing that in terms of the density matrix, one can see that in the replica limit, that function of the density matrix just becomes the trace of some normalized density matrix. So, so we can see that the constant that this quantity approaches is just equal to 1. Okay. So far things are good, and we're able to correctly see the limiting behavior. But then in principle, we can get corrections to this leading value of 1 from other primary operators and from the conformal block. But now we can argue that all of these remaining contributions should just go to 0 in the replica limit. Okay, so the way that we can argue for this is that we have a certain 4-point function of 4 twist operators, which are all different from each other. And we can also look at a different 4-point function where we essentially just reflect these first 2 twist operators. And the reason this is useful is that the same OPE coefficients which appear here will just appear squared in this 4-point function. But now you can again write down what this 4-point function is in terms of the density matrix. And that expression just goes to 1 in the replica limit. So it just goes to the trace of rho ABC, which is just identically equal to 1 in the replica limit. Okay, so this tells you that there should be no corrections from 1 in this quantity. So all of these OPE coefficients should just vanish. But then these are the same things which appear in this quantity. So this seems to be telling us that there should be no corrections from 1, no perturbative corrections from 1 in this OPE limit. Okay, so based on this, the conclusion that we would seem to draw is that the fidelity approaches 1 faster than any power of eta. And this would be a little bit similar to the behavior of the negativity in this eta going to 0 limit, where if you look at the negativity between A and C, where A and C are moving very far away, then the negativity approaches 0 faster than any power. But in our case, this result is not consistent with the numerics because we saw this very clean power law behavior as a function of eta for this quantity. Okay, so it seems that somehow, like in this argument, we are first taking the OPE limit and then taking the replica limit. And we seem to see that all the OP coefficients go to 0. But maybe if we first were able to somehow take the replica limit in the full expression and then expand it for small eta, we would not see this behavior. So anyway, so again, we don't have a full explanation of what is going on here. But one other thing is that instead of the fidelity, you could look at any of these alpha relative entropies, which I mentioned earlier. And you see that the same issue arises there. So this is somehow not specific to the fidelity, that we're able to exactly reproduce the behavior in the eta going to 1 limit, but not in the eta going to 0 limit.
So Shreya, in principle, what you could do, you could first, before you take this replica limit, you could take this limits where eta goes to 0, eta goes to 1, and eta goes to infinity first, and somehow determine the function f as a function of eta. And then you can take the replica limit. So if that might be interesting, you think.
So that is the order which we're doing here, right? Because we're first doing the OPE expansion and then taking the replica limit.
Yeah, exactly. So if you can determine the full function of as a function of eta first, before you take the replica limit.
So the thing is that seems to require using this Liouville action type of approach. Or there could be some other approaches which I'll mention later, which might be better because they don't involve replica tricks. But yeah, so this approach was difficult for the reason that I mentioned, that you don't get an analytic expression from it. One thing that we're thinking about now is that you could in principle, like, so for any integer values of these parameters, it is possible to just numerically find what this thing is, because, you know, as I mentioned, you get some polynomial equation of high degree, but you can always solve those equations numerically. And then we could try to do some kind of extrapolation from the integer values. Like there are some methods for extrapolation, and
I see.
We could at least then resolve some of the questions, like what is the, you know, which value of lambda does that give us, and or you know, does it give us some completely wrong answer, etc. And also, like, what is this issue with the OP limit? Yeah, but
what I'm saying that maybe if you just look, you said that you cannot get analytic formula for eta, f of eta, But instead of looking at any one of the limits, eta goes to 0, you can look at all of this together, like eta goes to 0, eta goes to 1, eta goes to infinity somehow. And then if you could somehow patch it up in a using some techniques or whatever, or some other, is it a possibility that
So what exactly do you have in mind for simultaneously looking at the limits?
no, somehow if you can guess the global function better, if you know the behavior near the singular points of, say.
But and why will the global nature of that function determine any local behavior near eta equal to 1? At the end of the day, yeah, you have a mega function, but its behavior near eta equal to 0 or 1 is going to be the same, like she wrote.
No, the eta goes to 0, eta goes to 1 has very different behavior, no? That's
Yeah,
not,
they are different, but yeah, I mean, I understand that. But what I'm saying is that she's focusing on the eta equal to 1 behavior, and how will global information help? I mean, that's what I don't see.
yeah, I know. Sorry, sorry for. I was just thinking that somehow if you could guess some function based on
Oh.
some limits
Yeah.
or something.
Yeah, you mean just make some guess for what f is?
Of, yeah, f is.
Yeah, I think
Yeah.
we've done some such guesses and tried to compare them to the fitting. And it works to some reasonable extent, but doesn't match exactly. So it's always kind of hard to say
Oh, I see.
how accurate that is. But yeah, we did try that. Like we just wrote down something simple which behaves quadratically in the eta going to 0 limit and has this logarithmic divergence in the eta going to 1 limit.
Yeah, exactly. That's what I was saying. I see. Okay, but that doesn't work that well. I see.
It
Okay.
works somewhat well, like, but it's not exactly the same as this. So even, you can do some best fitting of that. Like you can write such a function in terms of some unknown parameter, and do some best fitting of that, and it works close to the limits and doesn't work so well in between. So, I mean, maybe there's a better guess that we can come up with, but it's always hard to check if that's the actual function.
I see.
Yeah. Right. Okay. Yeah. So those were the results for these quantitative distance measures between. Oh, I am quite a bit over. But
Unfortunately, I have to end in like 5 minutes or so because I have to teach and I have to go and drive to office.
yeah, of course. Okay, let me just. I think in 5 minutes I should be able to cover some of the results here, which I think are interesting. So, so good. So, so far we discussed that there's some quantitative difference between rho ABC and rho tilde ABC. But now we can try to understand which parts of the reduced density matrices are actually different between these two states. So just from the definition of rho tilde, it's possible to check that for any state in any system, it preserves the reduced density matrices on A and BC. But the reduced density matrices on AB and AC are in general different between rho and rho tilde. Okay. So that means that it changes, like the rho tilde is going to miss some correlations between A and B in the original state and some correlations between A and C. And one thing we can look at is just the difference in the mutual information between rho ABC and rho tilde ABC. Okay, and the mutual information between A and C in these two states. And in some ways, this is a better quantitative measure of our original question about what are the correlations between A and C that are not mediated by B, because yeah, it's basically capturing which correlations we were not able to reproduce in rho tilde by acting just on B after tracing out C. Okay, so this quantity is UV finite, but it's not universal. And you can see this from the fact that this will not be genus 0. Both of these are non-genus 0 quantities. And we can also see this numerically. So we can look at the free fermion and Ising CFTs, which have the same central charge, but different operator content. And these red and orange plots are for delta IAC in these two models. And we see that the behavior is non-universal. Okay. But now we can again look at the OPE limits of this quantity. And if we look at the eta going to 1 limit, then we see that the divergence that we saw in the distance measures, which were telling us that rho ABC was very different from rho tilde ABC, are also reflected in this difference in mutual informations. Okay, so this mutual information difference diverges in this limit, which tells us that in this limit, there are a lot of correlations between A and C, which we were not able to reproduce in the state rho tilde ABC. So this suggests that in this limit, there is a sort of like the simple bell pair type of model for the correlations between A and C might actually be a reasonable model. Okay. We can also look at what happens in the other OP limit. So now if we consider the case where A and C are very far from each other, then we find that this mutual information difference looks like eta to the power of 1 plus 2 delta, where delta is the dimension of the lowest dimension primary operator after the identity. And this is interesting because if you look at the leading behavior of the mutual information in this limit, then that is just eta to the 2 delta. Okay, so the fact that this is a higher power tells us that the leading behavior of the mutual information between A and C precisely agrees between the state rho ABC and rho tilde ABC. So whatever correlations are being captured by this leading behavior are exactly of the kind which are mediated by B and can therefore be reproduced in the state rho tilde. So somehow this is telling us that there's not just a quantitative change in the entanglement between A and C as we go from the near interval to the far interval limit, but also some qualitative change in that. In the near interval limit, there are direct correlations, and in the far interval limit, they're mediated by B. Okay. Yeah, and then we can also look at, like I mentioned, it's not just the state on rho AC which changes, but also the state on rho AB. So we can see to what extent the correlations between A and B are lost in going from the original state to rho tilde. And one interesting thing is that in the eta going to 1 limit, that is the limit where B just is disappearing. So naively, you would have expected that any quantity like the mutual information difference between A and B should just vanish in this limit because B just doesn't exist anymore. But instead, as you can see from this plot, and you can also see analytically, this quantity actually approaches some non-zero constant in this limit. Okay. And this seems to be happening because of a competition between two effects. One is that B is becoming really small in this limit, but at the same time, the distance between the states rho ABC and rho tilde ABC is diverging. So there seems to be some competition between these two facts. And as a result, this quantity just approaches some non-zero constant value. So unlike the distance measures, it's no longer diverging, or unlike this mutual information difference, but it also doesn't just go to 0. Yeah, and you can also look at the opposite limit, where one interesting feature is that the distance between the two states, rho and rho tilde, in this limit is dominated mostly by the correlations between A and B rather than the correlations between A and C, because this delta IAB is much bigger than delta IAC in this limit. Okay, yeah, I guess, yeah, so I think it's been about 5 minutes, and yeah, maybe this is a good place to wrap up. So yeah, I guess I can just leave some future questions.
Yeah, maybe you can conclude with some like.
Oh, okay. Yeah, actually, do you say 2 minutes? Because then I could, actually 2 minutes is not enough to mention the thing about the C theorem. But yeah, so I guess some further questions besides the various puzzles that I highlighted during the talk are whether this quantity has some holographic dual, which is relatively simple. So either for the fidelity or the relative entropy, if we can identify some holographic dual, it's possible that that could give us some easier way of computing these things, or it might be a lot harder. It's hard to say. But in any case, we have some concrete predictions that we can try to compare to any gravity calculation. Yeah, and we can also ask whether the differences between these states can provide some new insight into other kinds of states which have long-range entanglement, such as topological phases, or the kinds of states that we get from non-equilibrium dynamics. Yeah, and more generally, we can ask, like in all the cases that we saw here, the inequality between the conditional mutual information and the fidelity was not saturated. So is there some general statement that can be made about classes of states where it is saturated, and do they have some interesting structure? Yeah, so thank you.
Thanks. Thanks for this very wonderful talk.
Thank you.
Thanks a lot for all the questions.
Yeah, so I have just only one. Okay, first of all, I should ask if there is further question, and I have only one. First, others should.
None from me.
Anybody else? Okay, in that case, let me ask my question. So this, what seems to be the most puzzling part of this thing is that, or that required that there's a sharp monotonic dependence for any eta on lambda for this fidelity. So this is seem to be a very interesting thing to understand, right? And there should be some physical interpretation for.
Yeah, right. I guess one alternative place where you could try to calculate this is just some free fermion type of model, because we know it's the same function in any CFT. And in free fermions, we have somewhat stronger techniques using the correlation matrices. So yeah, we tried to do this a little bit, but it does end up being quite a complicated expression. So I don't know, that's one place where we could try to understand things like the lambda dependence and the analytic expression. But yeah, I think any understanding, even on from some general argument in quantum information theory, if we could understand why it depends on lambda, that would be interesting. And also this feature of it being maximized at lambda equal to 0. Which basically tells us that this twirled Petz map was not necessary. We could just have used the simpler Petz map.
Yes.
Yeah.
That's yeah, indeed. Yeah. Okay, so thanks again for this great talk, and I officially close the recording.
Right.